So you know I like Python, right? And I like electric fields, I like dipoles, and I derived the far field approximation for the electric field due to the dipole. Now I want to make a three-dimensional representation of the electric field around the dipole using GlowScript VPython, and that's what I'm going to do. So I'm going to start here on the paper, and I'm going to work through the whole thing. I'm doing this from scratch. I have the basic idea of what I want to do, so there's going to be probably some problems, but I'm okay with that if you're okay with that. Also, just a reminder, I'm still working on setting up this whole video setup, and it may not be perfect. So if you find something that's not quite working well for you, let me know, and I can make things better. Hopefully not worse. Okay, so let's get started. Let's go over the paper. I'm going to turn off this video because it distracts me. There. Okay, and I'm going to move the microphone. Hopefully you can still hear me. So here I have a dipole. So a dipole consists of, oh, and I don't want to see that or that. There. So a dipole consists of two equal and opposite charges separated by some distance s. And I want to find the vector value for the electric field due to this dipole. It's some location. I'm calling this RO for the observation location. So how would I do that? Well, the very first thing is to realize that the electric field due to a point charge is 1 over 4 pi epsilon naught, that's just a constant, Q, which is the value of the charge, R hat, which is a vector in the direction of the, which is not this R hat, from the point, here's actually point charge, and here if I have observation location, that's R for 1 point, and that would be R hat. And then I divide by the magnitude of this squared, and then that's my electric field. So in this case, if that's a positive charge, the electric field would be like this. But what do I do if I have two charges? So if I have two charges, I have to do this twice. I have to do this once for the positive charge and once for the negative charge. And I did that analytically for along the axis right here, but what if I'm at some weird point up here? What do I do? Well, the first thing to do is to find this value right here. I'll call this R plus vector. Now, how do I find that value? Well, let's say that this, I'm going to call this RQP. Now, you have to mind your Q's and P's and actually separate these two. Mind your Q's and P's. Get it? I just made that joke up right now. So if I know RQP, I do, because if this is centered at the origin, then I should switch back to black. Then RQP is going to be the vector s over 2, 0, 0, right? Because if this is 0, 0, and this distance is s from here to there, then this is s over 2, so that's my value. And if I know some observation location, which it can be anything right there, then what's this vector right here? So it starts at the charge and ends at the observation location. So R plus is going to be RO, the final, minus the initial RQP. So I can find the value for R plus. And then I can calculate E plus as this. E plus is going to be 1 over 4 pi epsilon naught R, a Q, that's the positive charge, R plus vector divided by R plus vector cubed. And that would be the vector value of the electric field at that location. Well, what do I do after that? Well, then I just do the same thing for the negative charge. Now let's just go ahead and write down RQN for the negative charge. That's going to be equal to the same thing. I start from here and I go there. It's going to be equal to negative s over 2, 0, 0. So R minus is going to be equal to the vector RO minus RQN. And so let's draw that in here. So this is my RN, R negative. And then the electric field, this is the negative charge. I'd have to make sure I put in a negative value there. So this is actually going to be an electric field going this way, E minus. This is going to be an electric field going this way. It's going to be a little bit bigger because it's closer, E plus. And then the total electric field is just going to be the vector sum of those two. And that's how I could find the electric field at some arbitrary location. Now, there's two things. One, I want to do it at a whole bunch of locations. But before that, I have to realize, if I want to draw this as an arrow in VPython, in GlowScript, then I'll make an arrow object and I have an axis. And I can use the electric field as the axis. But if, let's say I calculate the magnitude of the electric field as 10 to the third newtons per coulomb. And this distance is a millimeter. And if I plot this electric field to say electric field, then it would be 10 to the third meters long because I'm plotting a distance. I'm drawing an arrow in distance. And so it would be ginormous actually, and I don't want that. So I'm actually going to have this other value in there called e scale. And let's say e scale is 10 to the negative fifth. And so if I multiply e scale times the actual vector e, then I can plot that. So I need to make a correlation factor between the actual electric field and the size of the thing I'm going to plot. I did quotes like that and you couldn't see it, so I'm doing it down here. Okay. And I'm just going to guess at that. It's not a big deal. Okay, so that's the first thing. The second thing is, how do I plot this? So let's redraw this this dipole. Now imagine that I draw a circle around my dipole. And I want to plot the electric field here, and then here, and then here. So I'll have the electric field over here is going to be this way. Once I get up to here, I know the electric field is going to be going that way. So it's going to have this shape that I want to plot. But how do I move to these different points? I could do it manually and just say, what's this value, what's this value, what's this value? But instead, let's do this. Let's say I have a circle of radius big R, and then this is the angle theta. Then what would the x and y value of this point? This would be RO is the observation location, would be equal to R cosine theta, R sine theta, 0, right? Because this is the y component would be the sine of that triangle, and this is the cosine of that triangle. So I can, based on just that angle and the radius r, I can change just the theta and I'll get different points on here. So now what do? So I'll say theta, and then the next one's going to be, actually let's call this delta theta. And then this will be 2 delta theta. So if I'll break this into equal angles, I can move around here. I'll start off with theta equals 0, and then delta theta is going to be 2 pi over n, where n is going to be the number of dots I want to have. So let's say it's going to be, I don't know, 7, 8. I don't know, n equals 8, maybe. I don't know, we'll play around with that. We'll get that to work. Oh, what happened? Oh, crap. Okay, well, the camera shut off, but I was done anyway. I'm going to switch over here. I don't want to stop because I already did this once. I'm going to switch over here to computer view. That works. Okay. I think my battery died. I told you I'm still learning this whole thing, right? Okay, so let's get to it. I've already started a little bit here. I put in my value for S and Q and K, where K is 1 over 4 pi epsilon naught. So the first thing I'm going to do is to draw these two charges. So I'm going to say Qn. That's the negative charge. It's a sphere. Its position is going to be equal to vector negative S over 2, 0, 0. Oops. And its radius is going to be equal to, let's say, S divided by 10. Let's see if that looks okay. S divided by 10. And then just to make them different colors, let's make them cyan and yellow, because those show up really well. So color equals color dot cyan. And let's run this. I always like to run it that first time, because you never know what's going to happen, especially with the sizes and stuff like that. Okay, there's that one. Okay, now let's draw the positive sphere. Let's make it yellow. So QP is going to be sphere position equals vector S over 2, 0, 0, radius, oops, comma, radius equals, and I'm going to give you the code, you know that, S divided by 10, color equals color dot yellow. Now we can really tell if they're too close or too big or whatever. Why is it so slow? Oh, I think that looks good. I can make them a little bit bigger, but that's fine. Okay. Now let's start giving it some properties. So let's say qn.q. I can actually give it the charge on qn as, I don't have to do this, but I'm going to do it. It's going to be negative q, qp dot q equals q. Okay, now let's just pick an observation location and draw one electric field, and then we'll go fix it and put a whole bunch. So I'm going to say RO. Let's say this R. How big is the radius of my circle? If I have a 1 millimeter difference between them, let's say 5 centimeters. Let's try that. So let's say R equals 0.05, and theta equals, let's say 25 degrees. So 25 times pi divided by 180. And so now I can say RO is going to be equal to R times the vector cosine theta, sine theta, 0. And I don't need to run that because there's nothing to run. Now I'm going to calculate E plus. I'm going to do it all in one step. It's going to be K times QP dot Q, that's the charge, times, I should find RP and RN. So RP is going to be, just like I said before, let me get my sheet to make sure I write it down right. R plus is going to be RO minus the location of the positive charge, which is going to be QP.POS, right? Because that's an actual object. I don't need to rewrite a vector for that. I can just write it that way. And R negative is going to be RO minus QN.POS. So this is going to be K times Q times RP divided by the magnitude of RP cubed. And remember, mag is a built-in function in GlowScript that returns the magnitude of a function, of a vector, and then star star is raised to the power. Let's just print this out and see if things are working. Let's just print EP. Okay, I think that's right. I don't really know for sure, but that seems fine. So I don't need to print it. Now I need to do the negative electric field. So I'm going to do the exact same thing. En equals K times Q n dot Q times Rn divided by mag Rn cubed. And then E is EP plus En. Print E. Again, just to make sure that things are working correctly. Because you never know. You just absolutely never know. Okay, so it gives me a value. I think I'm pretty happy with that. Now we're going to make an arrow. So E arrow equals arrow. Sorry. Okay, hold on. State. Okay. What the heck? Option state in a meeting. Okay, it's in a meeting. Okay. Arrow is an arrow type of arrow. I apologize for the interruption. Sometimes things happen. And the position that's arrow is going to be RO, right? I want not R0, RO. And the axis, let's just draw this first way. If I say the axis is equal to E, and I'm going to leave it as, oh goodness, I'm going to leave it as white. Or gray, I think it's gray. I'm going to just put the axis as E and let's see what happens. And there you go. I think that's in the wrong direction. I feel like that's in the wrong direction, but it's kind of hard to say. So you see here the problem. I need an E scale here, E scale. I know that it's going to be on the order of 100, and I want it to be smaller than that. So let's say E scale equals 1e to the negative 4. And then down here, I'll say axis equals E scale times E. Let's run it. And we can always make that smaller. Okay, but now I can't see the charges. I'm not sure what happened. Oh, you know what? I know what I did wrong. Okay, so what I did wrong was RO is too far away. So where's RO? So R, let's change this R to 1. Let's just try that, see what happens. Okay, now that's too big. So let's make this E -5. Run it again. It's still too big. E -6. Okay, now it's working. But again, there's my charges down there. They're too small. So I actually just need to go down to 0. Let's make this 0.06. And I'm going to have to make this even bigger. 7. Or, I mean, even smaller. Okay. I think that's pretty good. I should make these divided by, make these bigger. Twice as big. There, I think that's pretty good. So there's my 2 dipole, there's my 2 charges, and there's my value of my electric field. And I think it's working, right? Because if that's the positive one, it should be pointing more away from that one. And that's the angle, 28 degrees. I think everything's working very well. So let's go back up here and put theta equals 0. And now I'm going to say I'm going to say n equals, let's try 8. Let's see if this works. And then so d theta is going to be my step size. It's going to be 2 times pi divided by n. And now I can say while theta is less than 2 times pi, do the following. Step number 1. See, you notice the trick here. I already calculated an RO. I just have to change theta. I have theta is equal to 0 up here, so this is going to work. This line is still good. This line is still good. I'm just putting them in the loop. E scale, I can take that out. I mean, I need it, but I don't want to change that anyway, so it shouldn't be in the loop. Let's put it up here. There are other ways to calculate E scale, but, you know, what works, works, right? Doesn't have to be perfect. And then E arrow. Now, you know, I'm going to be making multiple E arrows. So I think it will work. I think it'll just redraw it, but it may be a problem. Let's just try running this. I can't remember. Oh, but this would run forever. I don't want to do that. So the next thing I want to do is move theta. So theta equals theta plus d theta. Let's run it. Check that out. That actually worked. Okay, my scale's too big. So let's make this. Okay. It's a little bit too small now, so let's say 3 times. Okay, I'm pretty happy. I'm very happy. Now, one thing you'll notice here is that it starts at the beginning of the vector. So this is the circle right here, right? And so this is exactly what it should look like. Let's see, 1, 2, 3, 4, 5, 6, 7. It has 8. I'm very excited about that. Let's change into 16. Okay, that's pretty cool. Now what can we do? Okay. Now, if you want, you could do the following. And I'm going to stop here because I'm pretty happy with this program. Actually, although I really want to do one more. I think I'm going to. Okay, let's go down here and let's say that made a loop in the X, Y plane. I want to do in the X, Z plane. Is that right? If I want to go in the X, Z plane. Yeah, so let's say theta equals 0. And let's just start over. And I'm going to copy this whole thing and post it down here. I think I didn't copy it. Control C. Control V. Okay. But now the only difference is instead of in the X, Y plane, I'm going to have this in the X, Z plane. That's the only thing I'm changing. Now I'm just moving the location of my observation. And I think it should all work. I think it should still work. And now I'll have 2 circles of electric fields. Please work. Check that out. Okay, come on. Is that not awesome? Oops, yeah, I can make it bigger. I mean, that's just art. That's the mapping out the electric field around a dipole. Now, if you wanted to, you could make another ring a little bit further away or closer in. Now, you are going to have a problem if you make a ring too much further away. The arrows are going to get super small. If you make them too close, they're going to get super big. So I'm happy with this, and I'm going to stop here. So I'm going to link the code down below. I'll be sure to include a tutorial on calculating the electric field due to the dipole. I think I might have something about drawing things in VPython too, but this is what makes GlowScript so freaking powerful, is that you can do these things. And I apologize for the camera cutting out in the middle of that thing, but I think we'll be okay. And let me know if you have any questions.